Auxetic materials are a fascinating class of materials that, unlike most materials, expand laterally when stretched and contract when compressed. This counterintuitive property, known as a negative Poisson's ratio, makes them highly sought after for various advanced applications, from protective gear to biomedical devices. Research into auxetics has significantly advanced in recent years, driven by new manufacturing techniques, material design innovations, and expanding potential applications. Most materials have a positive Poisson's ratio. They thin when stretched and thicken when compressed. Auxetic materials, however, display the opposite behavior. When these materials are stretched, they expand perpendicular to the applied force, resulting in unique mechanical properties. For example, auxetics can absorb more energy during deformation, making them excellent for applications where impact resistance is critical. Their ability to distribute stress evenly makes them resistant to fractures. Auxetic structures can withstand localized forces better, making them useful in wear-resistant materials. Let us look into recent advancements in auxetic design and fabrication. One of the most notable advances in the field of auxetic materials is the use of 3D printing. Traditional manufacturing techniques were often limited by the complexity of auxetic geometries. However, recent developments in additive manufacturing or 3D printing have enabled the creation of intricate auxetic structures, allowing researchers to design and fabricate materials with precise negative Poisson's ratios. This has opened up possibilities for customizing the mechanical properties of auxetic materials to meet specific needs in industries like aerospace, automotive, and biomedical engineering. The concept of metamaterials has gained traction in recent research. Metamaterials are engineered materials whose properties are derived from their structure rather than their composition. By designing auxetic lattice structures at both the macro and micro scales, researchers have achieved superior mechanical performance and lightweight properties. These structures are particularly useful in energy-absorbing applications such as helmets, automotive components, and even sportswear. Another exciting development is the introduction of programmable auxetics. These materials can change their Poisson's ratio in response to external stimuli like temperature or electric fields. For example, shape memory polymers can be engineered to exhibit auxetic behavior at certain temperatures. This programmable nature allows auxetic materials to be tuned for different conditions, making them adaptable for real-world applications. Nature has long been a source of inspiration for the development of auxetic materials. Researchers have drawn on biological structures that display auxetic properties, such as the skin of certain animals, to develop synthetic versions. For instance, the cellular structure of the skin of catfish exhibits auxetic behavior, and understanding this has led to bio-inspired designs for flexible, tough materials. These bio-inspired auxetics are particularly useful in the fields of soft robotics and wearable technology, where flexibility and durability are paramount. Recent research has focused on making auxetic materials that are multifunctional. This means combining auxetic properties with other desirable traits such as conductivity, magnetism, or thermal insulation. By incorporating conductive materials into auxetic structures, researchers have developed materials that could be used in flexible electronics or smart sensors. This combination of properties is promising for applications in industries where both mechanical and electrical performance are crucial, such as aerospace and defense. One of the most promising fields for auxetic materials is in the medical sector. Their ability to conform to irregular shapes and distribute pressure evenly makes them ideal for stents, orthopedic implants, and prosthetics. For instance, auxetic stents can expand uniformly when inserted into arteries, reducing the risk of damage. Similarly, orthopedic implants designed with auxetic structures have been shown to promote better load distribution and healing in bone tissues. The enhanced energy absorption and indentation resistance of auxetic materials have been leveraged in the design of sports equipment like helmets and padding. Companies are beginning to integrate auxetic materials into athletic wear and gear, providing athletes with better protection against impact-related injuries. Similarly, in military applications, auxetic materials are being considered for body armor, offering improved protection while maintaining flexibility and comfort. The aerospace and automotive sectors are exploring auxetic materials for lightweight, energy-absorbing structures. For example, auxetic honeycomb panels are being tested for use in aircraft and spacecraft, offering the potential to reduce weight while improving crashworthiness. Similarly, in the automotive industry, auxetics are being considered for use in car bumpers and other safety components to enhance passenger protection during collisions. Auxetic materials are being integrated into seismic damping systems for buildings, bridges, and other structures. Their unique ability to distribute stress and absorb energy makes them well suited for applications where impact or vibration control is essential. Researchers are also exploring their potential use in smart materials for adaptive architecture, where building components could change shape in response to environmental factors such as temperature or pressure. While auxetic materials hold great promise, challenges remain in their large-scale implementation and improvement in consistent quality while it is 3D printed. However, ongoing research and the integration of machine learning into material design are helping to address some of these challenges. Machine learning models can predict the behavior of complex auxetic structures, helping to optimize their design for specific applications. Thank you for watching this video. I look forward to seeing you in another intriguing episode. Until then, take care and goodbye.